Hi everyone, I'm Ping Wang from Princeton University. Today I'm going to talk about my recent research, the all-in-one matrix coupled magnetics for PWM power conversion. Magnetic components play a very important role in power converters. They provide various functions like filtering, galvanic isolation, and voltage conversion. Traditionally, magnetics of different functions are implemented individually as discrete components, as shown in this prototype. Discrete magnetic components take up a large portion of the converter size. Coupling multiple inductors and transformers with a shared single core can offer reduced component size, increase the level of integration, and higher converter efficiency and power density. Generally, there are two fundamental ways of coupling magnetic components, series coupling and parallel coupling as shown in the first two figures. In series coupling, the windings with voltage relationships are coupled by a single flux linkage. Example is the transformer. In parallel coupling structure, windings with current relationships are coupled by the flux linkage in parallel coax. Example is the coupled inductor in multiphase converters. In this project, we present a matrix coupled magnetic structure that combines both the series coupling and parallel coupling for PWM-operated inductors. Following topologies are several examples that can implement matrix coupled inductors. In each topology, the two inductors of one phase have identical voltage waveforms, so they are coupled in series on the same core leg with identical number of turns. Multiple phases on different core legs are coupled in parallel and are operated in an interleaved manner. The goal of this project is to integrate all magnetic components into one, based on their voltage or current relationships. We have done a systematic analysis of the current ripple reduction mechanism based on the superposition. Figures on the left are several equivalent magnetic models, and our analysis is performed based on the inductance dual model. The figure on the right shows the superposition procedures. The inductance dual model circuit can be split into multiple superposition subcircuits. Each of them has only one voltage source on. Adding up those subcircuits, we can obtain the winding current ripple of the matrix coupled inductor. Detailed derivations and procedures can be found in the paper. Another important performance matrix is the transient speed. If the parallel phases are controlled with identical duty ratios during transients, all the windings will always have identical square wave voltages with the same amplitude and pulse width. Therefore, applying switching cycle averaging to the inductance dual model, the averaged winding voltages are the same, regardless of phase shifts. It means, in the averaging model, all the windings are driven by identical voltage excitations, so each winding can be modeled as a separate inductance network as shown here, and we can get the equivalent inductance seen at each winding accordingly. This equivalent inductance determines the transient performance, so we define it as transient inductance, LTR. This analysis also implies that the switching cycle average dynamics of the converter with the matrix coupled inductor are the same as with discrete LTR. So the converter dynamics, like large or small signal models, can be analyzed by replacing the matrix coupled inductor with the discrete LTR as indicated in this figure. To quantify the matrix coupling benefits, we define a figure of merit that compares the current ripple of the matrix coupled inductor to that of discrete LTR. So this comparison is based on the same transient speed. The four figures here show the ripple reduction ratio with different phase numbers and coupling coefficients. The results indicate that stronger coupling and higher number of phases lead to lower current ripple and larger benefits. To validate the matrix coupling concept and the current ripple reduction analysis, a four-phase matrix coupled synchronous SEPIC converter was built. This slide shows the hardware prototype and the magnetic structure. The converter measures 3.5 cm by 3.5 cm in area and is designed to deliver power arbitrarily from 1 to 5 volt input to 1 to 5 volt output. The matrix coupled magnetics is implemented as a PCB planar magnetics, and this graph shows its PCB windings which are interleaved to reduce the AC resistance. This slide validates the functionality of the matrix coupled converter. Here are the operation waveforms. The blocking capacitor voltage can maintain very stable, and the winding current ripples are well balanced across different phases. Compared to the commercial discrete inductors that have similar current rating and current ripple, our matrix coupled inductors can reduce the volume by over 4 times. The matrix coupled SEPIC can deliver power up to 430 watts from 5 volt to 3.3 volts. According to the previous analysis, converter dynamics of the matrix coupled SEPIC can be analyzed by replacing the matrix coupled inductor with discrete LTR. Then existing modeling methods for a SEPIC converter can be directly applied. Here plots the small signal circuit model of the 4-phase matrix coupled SEPIC. Each phase is modeled based on the conventional SEPIC converter with discrete inductors, and small signal circuits of multiple phases are connected in parallel. Accordingly, the small signal control-to-output transfer function can be derived. Here, we compare the body plots of the modeled and the experimentally measured transfer functions, and they have a good match. This slide verifies the analysis on current ripple reduction. The matrix coupled SEPIC is tested under both interleaved and non-interleaved operation when converting voltage from 1 volts to 3.3 volts at 1 MHz switching frequency. As shown in the figures, the inductor current ripple under interleaved operation is only 0.8 amps, while on the non-interleaved operation, it will increase to 15.5 amps, indicating over 20 times reduction. We compared the measured results with the calculated results, and both the current ripples and the reduction ratio match well. That's all for my presentation. Thank you.